all very excited to have the final installment and finally learn about artificial intelligence. So, you know.
Okay, thank you. So I have two goals with this talk. So one is to illustrate some of the models we've been talking about, abelian sandpile and activated random walk, and also stochastic sandpile, which kind of sits in between them. And thought instead of just showing you simulations that are made with my own code, I will ask language models to generate the code that runs the simulations. And this process is very kind of eye-opening. It's a different paradigm for coding. And going through the process of like language model assisted coding really kind of pinpoints a lot of potential future safety issues with artificial intelligence in general. And so I will also touch on many of those issues. Okay, so I'll start with just the current state of AI in 2024. Then I'll talk about what I mean by AI safety. And then I'll talk about how math can potentially contribute to AI safety and how math education can contribute. I like to start with a poll. So this came from an online version of the talk where you could just click your response. But since we're here in person, why don't you hold up a number of fingers between 1 and 5? So 1 is for what, and 5 is for can't function without it. Yeah, okay. 3s and 4s, right. Yeah, that seems about the current state of mathematicians and how much they use language models. What you might be surprised to learn is that a lot of coders, like software engineers, are in category 5 at this point. Can't function without it. It's become a very useful and sometimes indispensable coding tool. Okay, this is sort of ancient history at this point, but GPT-3 was the precursor to the current ChatGPT, and it became a kind of game on social media to like play gotcha with GPT-3, and it's a very good pattern matcher. So in its training data, there are lots of proofs that square roots are irrational, and so if you ask it to prove that a square root is irrational, it's like, oh, I know what to do. Yeah, I can do that. And this proof would be like basically verbatim correct if you replace 4 by 3. But it just has this one crucial step that fails since 4 isn't prime, and the model seems like blithely unconcerned about that. And what I find particularly amusing is the follow-up. Are you sure that the square root of 4 is irrational? Can you tell me the value of the square root of 4? And I mean, at this point, it's a little bit surprising. A human, if you ask them, are you sure? What's the value? They would kind of take the hint that maybe there's something wrong with what they said previously. But the model really doubles down here, and it says the exact value is approximately 2.000, but this is an approximation since the square root of 4 is irrational. So one thing I want to stress is that this kind of mistake, it's funny when we know the ground truth, but in applications where we're asking a question that we really want to know the answer and we're uncertain of the ground truth, this kind of false certainty is potentially really problematic, right? And we can reason from the way the model is trained why it tends to do these sorts of things, like double down on false answers. I'm going to come back to that point. So that was only 2 years ago. Have things gotten better? On the plus side, Google's alpha proof and alpha geometry models solved 4 problems on the most recent IMO. And if you just look in isolation at some of the problems they solved, it looks very impressive. So this was a geometry problem on the IMO where you're asked to prove that these 2 blue angles add up to 180 degrees, and the red features were not included in the problem. So the red features are constructed by alpha geometry in its solution. So it extends this line segment BI to the point E, which is on the circle with radius LA, and that gives it a bunch of similar triangles that allows it to prove these 2 angles add up to 180. I mean, it seems impressive. There is some fine print here, so in order to do this, to produce this impressive proof, it wasn't enough to just give it the natural language description of the IMO problem. So, humans had to translate the problem into Lean, which is like a language for working with formal proofs. And then once it had the Lean statement of the problem, it was able to produce a formal proof in Lean. This particular problem it solved quickly, but some of the problems it took alpha proof 3 days to produce the solutions. And IMO contestants, human contestants, aren't given 3 days. So, there's some asterisks here, but still, it seems like progress. On the other hand, generalists, so those are specialist, systems that are specifically designed to produce math proofs. Generalist models still make some basic reasoning errors. So one of my favorite, we can actually demo this right now. So if you ask GPT to prove that there are infinitely many primes of the form 1001x plus 700. Okay, I asked O1. Okay, this will be interesting. It might actually get this. So, so this shows you how fast the field moves. So these slides are from August when O1, which is the current best model, didn't exist. And O1 is a model which does a lot of thinking under the hood before it produces its final answer. And I think O1 might actually get this. So, okay, so it realizes, it needs to find the GCD of these 2 numbers before it can proceed further. And it finds the GCD is 7, and so every number is divisible by 7. Conclusion, there are no primes of the form. Yeah. Okay, so this is a great example of 2 months ago, the state-of-the-art language model got this problem wrong, and now it nails it. Okay. Prove that square root of 4 is irrational. Okay. Okay, so nails that one too. it's not as impressive as it looks from these two examples. One downside to doing a lot of thinking before you answer is that, if your thinking initially leads you on a wrong track, then you get stuck in that track. So I have some examples of O1 doing that. But overall, things are moving pretty fast. It's still unclear from these examples whether a generalist language model is actually really that useful for anything. Partly because the error rate is still fairly high and it's hard to tell when there's an error. So I want to illustrate something that current language models are actually really useful for, which I call the copy-paste loop. And it's a way of using the language model as a coding assistant. So instead of writing the code yourself, what the copy-paste loop does is you tell the language model what you want the code to do. Let the language model write the code. Then there's this step that should all kind of give us pause, which is just run the code that the LM wrote. It might give an error. It might not even compile, right? But instead of trying to understand the code and debug it, copy-paste the error back to the language model and let it revise the code and repeat. And this will often lead to correct code after a relatively small number of iterations. And what's kind of alarming about it is that you don't really need to understand the code in order to execute this procedure. So let's illustrate this by drawing a sand pile. So okay, so this is what we're aiming for, this picture here, or a smaller version of it. So this is what you get in the square grid, Z2, by starting a large number of particles at the origin and then toppling until stable. So the toppling rule is the one from my first talk, where if you have 4 particles at a single site, then they spread 1 to each neighbor.
And the colors are the odometer modulo.
Right, so you can think of the colors as the odometer mod 4, or you could think of the colors as just how many particles are present in the final configuration. So each site at the end will have 3 or fewer particles. So there are 4, each pixel can be one of 4 colors in this picture. Okay, so let's ask a language model to draw this, and for variety, I'll ask Claude, which is a rival to ChatGPT made by Anthropic, which is approximately as good as ChatGPT and has a sort of more human-like personality, so I often prefer it. Okay, this was an experiment I did this morning, which I don't want to show right now, but yeah, here we go. Okay. Can you please write Python code that runs in Google Colab to draw an abelian sandpile of 10,000 particles started at the origin in D2. Please ask if you need clarification. Okay, so it thinks it doesn't need clarification. It's read a bunch of papers on sandpiles, so it knows what really a sandpile is. So now, copy-paste loop says, we could try to understand this code, but it's faster to just run it instead. And that's maybe a risky thing to do, is just run some unknown code, right? In this case, I'm offloading the risk onto Google because I'm not going to run the code on my machine. I'm going to run it in Google Colab. So Google servers will have to, do the, we'll have to assume the risk here. Let's see. Let's start a new notebook. Okay, paste the code. Let's see what happens. All right, looks pretty good. So sometimes the copy-paste loop will just work right away. This was an easy enough coding task that Claude just nailed it. Although, that's just my visual inspection, right? So a big problem with this method is well, how do you verify that the code is actually doing what you wanted? I mean, I've seen a lot of send files, and this looks accurate to me. Let's see if it can do stochastic sand file. So let's see. Leftmost, yeah, good. Okay, good job. Now make the couplings stochastic. Let's say it still takes 4 particles to topple, but they each go to an independent random neighbor, uniform over 4 nearest neighbors. This is actually probably more detailed than it needs, because if you just tell it random, it'll assume that you mean independent and uniform. So that's how the word random is used in natural language, and that's what it's trained on. Okay, so doing something. Go back to Colab and all right, so this is a little fishy because it's taking a while. Shouldn't particularly take longer to make a stochastic sand file than deterministic sand file. So let's make it smaller and see if that helps. And if not, then we'll, okay, good. So we drew something, okay, but this is a good illustration. We also got an error, right? So I don't want to debug this error because I don't even understand the code, right? So I'm just going to copy this error, take it back to Claude, and ask it to fix it. Okay. Okay, now we paste the new code.
This was the one with the 10,000 instead of the 1,000.
Right, yeah. We should reduce the number of particles to speed this up. Okay, so we get something. It's a little less clear whether this is correct. I mean, it looks approximately circular, which is what my conjecture from yesterday predicted, but it's quite small. So this is already a good illustration of we may have correct code for drawing a stochastic sand file, but how do we know it's correct? Okay, let's ask it one more thing. We'll ask an activated random walk question. So, okay, cool. Now, could
Can you ask Claude to prove it's correct?
let's ask it, sure. So can you prove your code is correct? It's unclear exactly what we're asking, but okay, so it's basically writing some tests to check that the total number of particles is conserved, the final configuration is actually stable. I mean, seems those are at least good things that you should check. So now can you sample from the stationary distribution of the activated random walk wired chain on, let's say, a 10 by 10 grid. All right, this is a somewhat harder question, partly because it probably doesn't know what this wired chain is, since it like only appears in a handful of papers. So we'll please ask if you need clarification. Okay, so this is good. Like, it knows what it doesn't know, right? So like, it's gonna clarify its understanding of activated random walk. It asks what value should I use for the sleep rate, because I didn't tell it that, and what wired means. Okay. Okay, good questions. So since I'm lazy to answer them, let's just upload a paper for it to read. So this seems like a good paper. Well, in theory, I already have a copy of this paper. Let's see what happens. Okay, that worked. Okay, so now I'm gonna just give Claude the paper. Questions, this paper answers them. Tell me if you still need any clarification. Oh, except for the sleep rate. Sleep rate 1. Okay. Okay, so it understands what wired means, that there's killing at the boundary, and for sampling we can use proposition 10, start with 1 active particle at each site. Okay, all right, looks promising. Let's see what happens. So if we should expect it to take this long. Okay. All right. So there's a 10 by 10 grid with, I guess the, I don't know if blue or white is the sleeping particles. I think blue because it's saying the density of sleeping particles is 0.32. Again, you know, that looks plausible to me that it did it right.
Does it look hyper-uniform?
It doesn't. This doesn't look particularly hyper-uniform to me. It even has some. Yeah. maybe it's hard to see the hyperuniformity in a small example. Okay, so, I mean, these are sort of toy examples because we could write the code if we wanted to ourselves. But copy-paste loop is actually really useful for doing things. Like, this is something I did last year during my sabbatical. It doesn't matter what it is, but I couldn't have done it without copy-paste loop. It spent about 6 weeks using the loop. And I'd say I understand about 80% of the code of the finished product. So it definitely comes at some cost, right? So there's something disturbing about this process that, you know, you can get code that works, but neither the human nor the language model necessarily understands why it works. And I mean, language models themselves, there's something almost biological about them. Like, you know, they you know, they have impressive capabilities, but also weird failure modes. So let me tell you about an interesting failure mode. Is this name Marjorie Eiskopf familiar to anyone? So it wasn't familiar to GPT-4 either. So if you ask it who is Marjorie Eiskopf, and tell it not to search the web, well, it doesn't like to admit that it doesn't know, but it kind of hedges by saying that she's not a widely recognized historical figure. Basically, LM speak for I have no idea. But what's interesting is if you ask it a different question, who was Isaac Newton's grandmother? And so someone pointed out, last time I gave this talk, I didn't instruct it not to search the web this time. So you have to take my word for it that it didn't search the web and just produce this response. Isaac Newton's grandmother was Marjorie Eiskopf. So it seems like it does know who Marjorie is. But the picture is actually very murky because, well, immediately after claiming correctly that she was Newton's grandmother, she then claims that she's his grandmother on the wrong side. So, and depending on exactly how you ask the question, it will claim either that it doesn't know, or that she wasn't a widely recognized figure, or that Marjorie was Newton's mother, or Newton's father's mother, or Newton's mother's mother. So, at least part of what's going on here is a phenomenon called the reversal curse, which is a basic failure mode of large language model reasoning. So the reversal curse in its pure form is the following phenomenon. You take a large language model and so it's already been trained on a ton of, you know, natural language data, and then you fine-tune it by producing a little bit more synthetic data to train it on. And these authors, the synthetic data they trained it on had a bunch of statements of the form A is B, like, you know, Newton's grandmother is Marjorie Eiskopf. Okay? But they didn't include any of the same facts reversed. So they didn't include any examples like Marjorie Eiskopf is Newton's grandmother. And what they found is that LLMs don't generalize. So if you give them a bunch of facts of the form A is B, and then you ask them the same facts, but when you ask them, is it true that B is A, they basically don't score better than random chance. And this is like completely flat across all sizes of models. So like, you know, GPT-2, 3, 4, like they all fail to do this kind of generalization. And you can ask, I mean, that's sort of surprising because they're capable of lots of complex pattern matching, and this seems like not a very complex type of pattern to predict. But you know, my theory of why this happens, you can see how it might happen if you examine how language models are trained. So I'll try to fit that on one slide, just a high-level view of how you train these language models. Because it's really, at its core, the idea is should be very familiar to probability statistical physics crowd. So, so you've got this large corpus of documents, and you decompose them into tokens. A token is a short word or a fragment of a longer word. And then you've got a prediction task, which is, so say I've got a document with tokens x1 through capital Xn, and I read the first n-1 tokens, and I try to predict the nth token. And so I think of my model, it's a complicated, it's a function of a large number of parameters, theta. And so for any particular choice of parameters, my model will give me a prediction for xn given the previous n-1 tokens. And then you want to score, well, how good was this prediction? And so the magic scoring rule is that you should take the log of the predicted probability of the token that actually appeared next in the document. So, like, if the document started, let's say the document is this slide, right? So my first 4 tokens are how language models are. Okay, and then it has to predict the next token. Maybe it predicts that the next token is trained with probability 10%. So then its score for that token would be minus log of 0.1. So that way you incentivize it to give high probability to tokens that actually appear. And then you just do gradient descent on this loss surface. So to think of theta is a vector with billions of parameters. Those are like matrix entries inside your model. And so each theta gives you a loss, which is like how good was that particular theta at predicting the next token. And you've got this a very hard to visualize loss surface in a billion-dimensional space. And you just flow downhill on that surface. So given your old theta, your new theta is given by subtracting the gradient of L at your old theta. And there are many fancy versions of this gradient descent that use momentum and other tricks to get better convergence. But this is the basic idea. And I think if somebody told you this idea back in 2010, then you'd probably be like, huh, okay, I don't know, seems interesting, I wonder what happens. But very few people would have predicted that you could get such good linguistic capabilities just from simple gradient descent procedure like this. Coming back to the reversal curse, the fact that language models are always trying to predict the next token from what came before might explain the curse. You figure the name Marjorie Eiskopf, since Marjorie is not a very, there's not much known about her except that she was Newton's grandmother, and most of the documents that mention her probably are about Isaac Newton, and probably Isaac Newton's name comes earlier in the document than Marjorie's name. And so it makes sense that the model would learn that, well, if it's a document about Isaac Newton, maybe especially about his childhood or his biography, then it would make sense to predict the token Eiskopf. But vice versa, if you don't have any documents where Marjorie's name appears first, then there's no reason to predict the token Newton coming after Eiskopf. Okay. So some kind of general takeaways from the first part of the talk are that, like, you know, we're already kind of approaching this phase of AI development where, like, you know, we're building digital minds, right? Like, you know, they do some form of reasoning. It's faulty in many ways. It's impressive in other ways. The ways in which it's faulty are like kind of different from the ways in which human reasoning is faulty. And I think like it's important to just keep in mind that like technological development it's not like a hurricane or something that's just, you know, a natural phenomenon that we are passively have to deal with. Like it's a phenomenon driven by humans. Like it's human researchers and human engineers that are ultimately driving the progress of this field. And I think like this is a good time for you know, humans as a species to just like step back and think about, like, now that we're able to start building minds, like, is it a good idea to do that? And what kind of minds does it make sense to try to build? And I think there's all kinds of views on this question. Like, there's definitely not consensus. So I've kind of broken it into 5 buckets. And like, you can find, you know, smart, thoughtful, principled people that endorse all 5 of these views. So if I had more time, I would give the sort of like short positive case for each of these views. But I think it's more important to like let you form your own views. So I want to invite you to like pick a view and debate your partner and try to come to consensus with your partner on like which of these 5 is the best way forward. Go. Also, like, a lot of the it's hard to control. It's okay to keep it. It's really hard. Of course,
Well, that's what I'm saying. I don't really hard time thinking about have the potential to improve my life.
This question, it's kind of in the very last phase of training. So it's trained in that phase not to although probably better at expressing opinions.
You don't have to use someone who stole some money from you or share about
So I'm really happy to hear all the debate. This is exactly what I wanted. I wish I could let it go on longer. So maybe over lunch we can keep going. So this is a statement that was signed last year by not only prominent academics, but also the heads of all the leading AI labs. Mitigating the risk of extinction from AI should be a global priority alongside other societal scale risks such as pandemics and nuclear war. So it shows you that all the leading people take this this risk or the possibility of this risk seriously, and it's kind of hard to think about. I mean, they're talking about like literally humans being driven extinct, and it's hard to reason about specific scenarios that would lead to that, when right now all we've got is these chatbots, right? Just like, how do you get from that to extinction? And my preferred way of thinking about it is to not try to reason all the way to whether extinction is how likely extinction is, but just think about disempowerment. Because it would be really bad if humans were just still around, but permanently disempowered. And disempowerment is something you could see already happening. There are all kinds of examples already, like a trading bot that outperforms a human trader, but the person who programmed the bot doesn't understand how it makes money. A recommendation system that's better than humans at distinguishing between military and civilian targets, but the officers in charge of targeting don't understand how it distinguishes. There's many examples like this, and the kind of incentives driving it are bad because either you use technology you don't understand, or you could refrain from using it, but then your competitors will use it and outcompete you. And so there's this kind of, as AI systems improve, there's this kind of bad incentives leading to deferring more and more to automated decision-making systems. And if you keep extrapolating that, one worry is that the global economy becomes just more and more incomprehensible to humans, and we end up disempowered. Okay. I guess I'll just end with flashing a slide about how math can contribute. I think in terms of the interests of people in this room, like the high-dimensional geometry of loss landscapes is something that is really important for understanding like how systems will generalize out of distribution. And there's a lot of mysteries in that realm that mathematicians could, I think, contribute to. And we should also think about how to help our students both succeed in a world that's going to be pervaded by AI and also contribute to steering that AI in a good direction. So I'll just end with this, repeating this mantra that tech progress isn't the force of nature, it's actually driven by human choices. And some of those humans are our students. Some of those students will go on to design the next generation of AI systems, so let's empower them to make thoughtful choices. Thank you.
Questions?
It's a comment. My impression that the reversibility curse also like happens to humans actually, not just AI. So maybe this is not that different.
Do you have an example of humans falling for the reversal curse?
I think like right now I can't think of a concrete example, but for instance there are like people like if you say the name of a country, he will give the name of the capital. But for some like less known countries, you ask where is this city located, he won't be able to say the other way around that it's in this city, in this country.
Yeah. Okay, so maybe we're not that different.
So one of the words, so yeah, I'm an AI safety researcher and not a math major. Thank you for the talk. This is amazing. I'm so happy to see like math people involved in AI safety. You're very needed. Something that we're worried about is that these algorithms become smart enough to start to do some of their own, like developing better algorithms and to make themselves smarter. Do you see that coming soon? Like when you're interacting with these machines, do you see them becoming intelligent enough to improve their own like training process? And if so, like what implications does that have for the field as a whole?
Yeah, I think with that question, so I think you have to break it down, inside an AI lab, there are many models, right? So, what we see from the outside is just, this one model or a few variants of this one model that we can interact with. But from the inside, what I imagine it looks like is, in addition to the main model and all of its different like training checkpoints and branches and stuff, there are all kinds of like sort of helper models that are used to curate the training data and augment the training data and figure out what is the best like regularization term for the loss and figure out what are the best hyperparameters and so on. So it's like you've got this giant system of a whole bunch of interacting ML systems, and it's unclear what self-improvement means in that context, right? So it's like, where's the intelligence located? Like, is it in the entire system of all these interacting components, or is it in one particular component? So I think, like, if you zoom in, it's not exactly self-improvement. It's like mutual improvement of a bunch of interacting components, with also some humans tweaking, the knobs of some of the components. So it's, I don't know, you won't get like pure 100% like autonomous self-improvement. There will be humans tweaking the knobs, but their influence will go down over time. So I don't expect, some like intelligence explosion, singularity type thing, but I do expect like the pace of change keeps increasing. Unless we regulate to slow down. And I think it's totally possible to do that, and that's worth thinking about.
I have a question. You've kind of focused on the risk and the dangers, but do you also see a potential for things actually being improved through the use of artificial intelligence?
Yeah, I do think there are potential futures where AI is a net positive for humanity, but they have small measure in the total space of possibilities. And so, like, our job is to like help steer the development of the technology toward those like, you know, little good islands in a sea of more negative outcomes. And I think we don't have good understanding of how to do that because it's a pretty unprecedented situation of like, you know, we've never as a civilization really tried before to like direct technological progress in a certain direction. You know, that's the kind of thing that like, it's possible to do, but we don't have much experience with it. So I think we should move slowly. Like, there's no rush. Like, we could get to those good islands, but it'll take a lot of research and time and careful experimentation. And there's no reason to just like rush and develop the best systems that we could possibly develop right away.
So yeah, I understand that we need to take some time to develop like the best AI model, but there are a lot of competitions in the labs. Like, is there a way to slow down things for everyone?
Yeah, it's a coordination problem. So, you know, it's very similar to problems like climate change, where you need a bunch of actors to all agree to refrain from developing as quickly as they could. And I mean, humanity has like a mixed record on coordination problems. Like, when you're in them and they're not currently solved, they seem hopeless. But like, there are examples of us solving them. Like the CFC emissions that depleted the ozone layer was a big problem in the 80s. And it was basically solved by an international treaty, and the ozone layer is recovering. There's also examples of humanity kind of collectively deciding, maybe unwisely, not to pursue certain technologies, even though they might be useful, like genetically modified organisms. You know, we mostly aren't using genetic engineering, even though it could be useful for many things, because like enough people have enough ethical qualms about it that it's just sort of a decision that we made as a civilization. And yeah, I don't think the number of actors that would need to coordinate is that high. You know, it's a few labs and a few governments. It's not that many actors.
I think we should save the discussion for lunch, and let's thank Lionel for very nice.